cuts us off from the changeless perfection of eternity.
This world is a place of trial for human beings. There's a degree of pessimism about the way the world is. And one can find that reflected in the language of the prayers used in the medieval monastery that was here before the Reformation. Every night before they went to bed, the last prayer that was said in that service asked God to protect them through the silent hours of the night, so that we who are wearied by the changes and chances of this fleeting world may rest upon thy eternal changelessness.
Well, erosion waits for nobody, it just keeps eating away. And we just have to keep working at it to try and hold it back.
Medieval man's divided attitude to time is summed up in their cathedrals. They were built as monuments to the changelessness of eternity. Yet it was recognized that time would inexorably grind even them away.
Durham Cathedral is a bit like a forest of oaks, saying, here is the permanence of God. The huge thickness of the pillars emphasizes solidity and permanence in dramatic contrast to our fleeting world.
It took 40 years to build the cathedral and 900 years to keep it in good repair. We could be fighting a losing battle, but we hope that whatever we replace will last at least another 100 to 200 years' time.
Medieval architecture and music were a celebration of God's permanence, but ironically, the study of these things, particularly music, began the transformation of the medieval mindset.
If you consider the people who were commissioning the building of cathedrals were also the same people who were commissioning music, they very much wanted to elicit the same emotional response from people with both these things. They wanted a sense of awe. Both were meant to be monuments to eternity. One is permanence in motion, and one of them's permanence at rest.
Just as architecture required the ability to unfold a structure in space, so music required the ability to unfold a structure in time. Music was one of the places where the mathematical and scientific understanding of time began.
If you consider what every well-educated man was, expected to know, it consisted of the classical quadrivium, which was constituted of geometry, arithmetic, music, and astronomy. So you can see that these things are very important things, and they all go together. They're considered together.
The medieval study of time in music and then geometry influenced the fledgling sciences of mechanics and astronomy.
There had been astronomy, which had investigated the heavens. The heavens are cyclical and perfect. They don't change. On Earth, though, everything changes, and it was thought by many people that things on Earth were not susceptible to mathematical analysis, and Galileo changes that. Galileo is one of the first people to make an adequate attempt to mathematize nature, and whereas the entire science of change, the entire understanding of the world that we lived in came under the general heading of motion, from chicken to egg and so on and so forth. What Galileo does is create a mathematized science of motion, so that he mathematizes the fall of a body and shows that one can mathematize it in a parabolic trajectory. And Newton just goes way beyond that.
Where the medieval mind had seen permanence, the Renaissance mind now saw change.
He thinks of a curve as a point being drawn out through time, and when the point moves across, it marks out a line. Curves, as it were, have their own velocity. You can express any curve in terms of the rate at which that curve is changing with respect to time. It's absolutely the most significant contribution to science that there has been.
Our lives are an infinite series of present moments. Moments which Newton used to calculate motion. Time, the agent of dying and decay, in Newton's hands becomes the agent of motion and progress.
The triumph of Newton is to link the celestial and the terrestrial. He shows that the law of universal gravitation applies to things happening down here on Earth as much as they explain the orbits of planets around the Sun, and that is a remarkable achievement.
Newton's science of motion and his mathematics of time underlay the technological revolution which propelled humanity forwards. Newton's idea that space and time together form a simple, rigid framework dominated all thinking until the final years of the 19th century. Then a problem occurred. Scientists experimenting with light found that no matter what they did to it, they could never alter the speed at which it travelled. This and other anomalies eventually led Einstein to his theory of relativity, in which he concluded that the speed of light is the only absolute constant, and that everything else, like space and time, are variable.
Einstein's special theory of relativity was really the death knell for the old concepts of space and time. Einstein showed that absolute space and absolute time couldn't exist any longer.
According to relativity, space and time were no longer a rigid framework, but were instead a fabric which could be stretched and distorted.
Einstein, in fact, had two theories of relativity. In one, he showed how time can slow down if you travel very fast, close to the speed of light. That was known as a special theory of relativity. In general relativity, he showed that time can slow down if you sit in a strong gravitational field.
Just as a magnet creates a magnetic field, so all massive objects create around themselves a gravity field. And just as a magnetic field affects objects within it, so a gravitational field affects not just objects, but light and even time, bending, stretching or compressing it. The The more massive the object, the greater the field it creates, and the more it bends space-time.
Imagine you approach a massive star. The closer you get to the star's gravitational field, the slower your clock will run. Even your biological clock, your whole concept of time will be running more slowly than it did further away from the star.
The byproduct of time slowing down is time travel to the future.
Both Einstein's theories of relativity say that travel into the future is allowed. In fact, we've proven it experimentally. One way is to travel very fast, so you'd head off in a rocket, travel at close to the speed of light and come back again. Because you've travelled very fast, your clocks will have run more slowly. And so if you've been away for 1 year according to your onboard clock, maybe 10 years have gone by on Earth. So in essence, you've travelled 9 years into the future. Another way of travelling to the future is to go and orbit a massive star. If you do it for a year, again, you may come back and find that 10 years have elapsed on Earth. So either way, time travel into the future is possible.
And this is a fact we have to deal with. Satellites orbiting the Earth do travel minutely in time. Because of the speed they travel, their onboard clocks gain milliseconds relative to clocks on Earth.
Time travel to the past, however, is more tricky. But despite that, Einstein's relativity says that it's allowed. It was shown half a century ago, in fact, that there are solutions to Einstein's equations. The mathematics shows that time travel to the past is possible.
One candidate for how time travel to the past might be physically possible was via one of the universe's more exotic features: black holes.
Normally we think of a black hole, or a collapsed star, as being a point of zero size and infinite density, surrounded by what's known as the event horizon, the point of no return. But most stars actually spin, and when they collapse, they will start to spin more rapidly. And a spinning star that becomes a spinning black hole doesn't have a point singularity at its center. Its singularity looks like a ring, like a donut. One possibility was that maybe we could travel into a black hole, avoid the singularity, and travel through the middle and come out the other side. Because space and time were linked, you would not only have to come out at another region in space, you could come out at another point in time. This sounds like it's the ultimate freedom for us, that we can travel both into the future and the past. Einstein's theory of relativity gives us this wonderful freedom of moving back, changing history, going into the future, see what things are like, and coming back again, finding out what mistakes we might make and avoid them. This would imply that the past, present, and future all exist. There is no present moment to distinguish past from future. All times coexist. Time just is. And so the future is already out there. The only way to understand this was to link the 3 dimensions of space with the 1 dimension of time to make what became known as 4-dimensional space-time.
Space-time is certainly different stuff from space, because it's 4-dimensional as opposed to 3-dimensional, which is a big difference. So it's just that time really has to be brought into the picture. It's one thing, which is space-time.
Let's imagine what this might be like. three-dimensional space implies a volume, and you can move anywhere in that volume. Once you add time as the fourth dimension, another axis, then this block of space-time would contain within it past, present, and future, all at once. Time is frozen, all times exist together. So just as you could say, over here, over there in three-dimensional space, you can talk about over then in four-dimensional space-time.
It's a way of looking at things, if you like, which physically we seem to be forced into. That is, when I say physically, I say from the point of view of what relativity tells us. And relativity is extremely well tested, something like 14 places of decimal. I mean, it's incredible. So that we know that this theory does describe the universe to an extraordinarily precise degree. So we have to take it seriously. And that theory tells us that we have to regard space and time as part of is one thing. It's all out there as one thing. In the same sense that space is out there, time is out there.
Like the medieval gods' view of time, Einstein's physics says the future is already out there. The moments of our lives just waiting for us to step into them.
But there's no more problem about the future being out there, in a sense, as there is with the space being out there. I mean, you say, Mars is out there, you see, and why is that any more comprehensible than, say, next week is out there? I mean, it's just as far away in a certain sense. Well, in a certain sense. Mars is still out there, but it's not something we're immediately accessible. We can't immediately access Mars.
If you take this block, four-dimensional space-time, literally, it means you have to abandon free will. It means not only is the future preordained, but it's already there. It's already happened. There's no point making any decisions. Whatever you do has already happened. If I choose to drop a stone into a pond, I think of it as being my free choice. But of course, in four-dimensional space-time, I had no choice in dropping the stone. The splash that is already there in the future, and so we lose all free will. If time travel were possible, then you can imagine people coming back from the future to visit us. There's no good us saying, you can't exist, you haven't happened yet. They've come from a time that they consider as their now, and for them, we're in their past.
So this means that the future and the past are all, in a sense, out there. And that also gives us a very deterministic view of the world. We have no control, if you like, of what happens in the future because it's laid out. I think the trouble people have with this idea is that you think of the future as being under your control to some degree. And so this means that if the future is laid out, then in a sense it's not under your control.
Personally, I'm very uncomfortable about the block universe idea. Now, this may just be a gut feeling, maybe irrational, but I can't accept that the future is already out there. I can't accept that I don't have any free will.
I think there is a positive side to this picture of space and time being laid out there as four dimensions, because in a sense it tells you that all times are there at once, and it can affect how one thinks about people who have died. I mean, I remember thinking in this kind of way when my mother died. In some sense, she was still there, because her existence is still out there in space-time, even though in the normal way of thinking at our time, she's not alive. colleague of mine, one of his sons died in tragic circumstances, and he was a relativist. He is a relativist. I mean, that's to say, someone who has worked in Einstein's general theory of relativity. And so I presented this view of things to him, and he found this reassuring. This was before I learned that Einstein had also taken the same line. When his colleague Besso died, Einstein wrote to Besso's wife, and in this rather reassuring way, to say that Besso was still out there in a sense, because space-time is laid out, and so it's somehow reassuring. I certainly think this way often. I think of somehow space-time is laid out, and therefore things in the past and things in the future are, in a sense, out there still.
But almost at the same time as relativity started gaining universal acceptance, a radically different picture of the universe was emerging.
The way out, if you don't want to accept the block universe idea, is quantum mechanics. Now, quantum mechanics is the other great theory of 20th century physics, and that states that the future isn't predetermined and preordained.
Quantum mechanics was born out of a series of experiments whose results even today have no satisfactory explanation. Relativity works at the large scale, where it provides exact predictions of what will happen next. But when physicists started looking down to the atomic and subatomic level, the familiar laws failed. At this level, there were no certainties, only probabilities. How can the future of the entire universe be already out there if the future of a single particle is so utterly unpredictable?
Before we look to check to see what the atom is doing, not only is there a gap in our knowledge, not only do we not know what it's doing, the atom itself hasn't decided what to do. If it had an infinite number of choices to make, it will be doing all those choices at once. And it's only when we look to see what's happening that we force it to make a choice. Quantum mechanics, the future is not determined. And so quantum mechanics, in a sense, rescues us and rescues free will.
In a sense, you don't have the future laid out in quantum mechanics. So quantum mechanics is basically different in the way we look at it. You do have, at least when the measurement takes place, you do have this indeterminacy about the future, and it's, in a certain sense, I suppose, the incompatibility with a picture of special relativity is a necessary feature of this, the fact that there is this indeterminacy and having, in a sense, incompatibility with relativity. The notion of free will is incompatible with relativity, as we understand relativity. It's not incompatible with quantum mechanics. In a sense, quantum mechanics, as we understand it, allows for this indeterminacy in the future, whereas with relativity there is a basic incompatibility. So I think that the way we understand these two theories at the moment, there is a difference in relation to how one views whatever free will is. Relativity is sort of inconsistent with it. Quantum mechanics is not. So we have these two great theories, both of which are extremely accurate, tell us something about the way the world operates, something very insightful and profound and accurate about the way the world operates, but they're incompatible with each other. So there's something missing, and there's no doubt about that. How important that is for such things as, for example, how we feel the passage of time, well, I think it is important.
The tragedy of modern physics is that it explains so much of the objective universe, but at the cost of what we subjectively feel, about our conscious free will and our perception that time does flow.
I very much think there's a flow to time. If you consider what music would be like if there wasn't a flow to time, You couldn't have music if you didn't have a memory, or if you didn't have an expectation generated from that memory. You'd have an isolated note in the now. Music unfolds in time in such a way that we have a memory of what we've heard, and this memory conditions what we expect. And this, of course, is something that everyone's familiar with, because if you hear, you have a very strong expectation that the next note will be. Music is a distillation or a side effect of that mental faculty we employ to perceive time and things changing in time.
The question of the passage of time, I think, is something that physicists have rather set aside and taken the view that, in a sense, it's not really physics. I mean, it's a subjective issue, and subjective questions are not part of science. Now, when you start talking about phenomena like one's individual perception of the passage of time, then that is a subjective thing. And that's almost a taboo subject for science, because it's subjective. The physical world is out there, and certainly the view according to relativity is it's sort of out there, and there's no flow of time, it's just there. Whereas our feelings, we have this feeling of a passage of time, and so it's something intimately connected with our perceptions.
We have this subjective feeling that time goes by, but physicists would argue that that is just an illusion.
Yes, I think there is the view that scientists, or physicists particularly, would tend to take, that somehow the flow of time, or our feeling of the flow of time is something, an illusion, that it's not really real in some sense. But it's certainly true of how we perceive time. And okay, what kind of an illusion it is, I mean, it's got something to do with our perceptions.
Illusion or not, our perceptions emerge somewhere between the cosmic scale of relativity, where the flow of time is frozen, and the quantum scale, where flow descends into uncertainty. Our world is on a scale governed by a mixture of chance and necessity.
I mean, this is my own view, which I'm going out on a limb here, that other people don't necessarily share with me, this particular view. But the view I have is that there is a kind of large-scale quantum activity taking place in the brain. Quantum mechanics doesn't necessarily say that quantum effects take place only very tiny. It's not just individual particles. They can involve large areas. And so the argument is that such a thing is taking place over large areas of the brain, and that our conscious perceptions, our conscious actions, our conscious willing has to do with that process. You're then bringing in an area of physics which is quite different from either our large-scale picture of space and time or our small-scale picture of quantum mechanics. It's a new picture which comes in just at that level. And I think you need a new picture to explain something like consciousness, which has a different relationship to time.
If quantum events are at the root of consciousness, then the same principle of uncertainty which governs the subatomic world might explain our ability to make apparently random choices. Opening up the future to the possibility of change would provide the first step of restoring to physics the flow of time it currently denies.
I don't think time flows. I feel that time flows, but I think the only way we can get a better understanding of this is to have a better understanding of how consciousness works. I think human consciousness probably has the secret as to how and why we think of time as going by.
I don't think we have the tools, not just the tools, we don't have the physical picture to be able to accommodate these things yet. It doesn't mean that I don't think we will ever accommodate these things within some kind of physical picture. It's just that we're not very close to it yet. Now, it may be that when we understand more about how quantum mechanics and relativity fit together, we'll see a passage of time out there also, not just within ourselves.